All right. Yes, that's the option you want. Okay, so just to recap briefly what we did yesterday. We talked about the caffeine experiment to see if caffeine really does change your pulse rate. I did this last year with my class, and these were the results that I had from the two groups. The group that had caffeine had an average change in their heart rate of 3.2 beats. And the group that did not get caffeine had an average change in their heart rate of 2.0 beats. And so we said the difference between those two groups was 1.2 beats. And then we wanted to know whether or not we had evidence that caffeine does or does not increase the heart rate. I mean, maybe, but 1.2 beats isn't very big. But I don't know how big of a difference we would need for me to say, oh yeah, it's definitely the caffeine. We have two possible explanations for the difference that we saw of 1.2 beats. Either it was the caffeine that did it, or it was coincidence. Because remember, I randomly assigned to my two groups, so all the other confounding variables were equally spread between my two groups. So you can't say, well, maybe the caffeine group just naturally had higher heart rates. My random assignment took care of that. So either this difference is because of the caffeine, or it was due to just coincidence, it was chance. We are going to assume that it was just due to chance. That somebody that saw a difference in their heart rate of 8 beats in a minute, this person was going to see that change in their heart rate no matter which group they were in. So if they had been assigned the no caffeine group, the 8 would have been down here. That this person right here, that had a lower heart rate before, or sorry, a lower heart rate after than before, if they'd actually had the caffeine, they still would have seen this difference. That's the assumption that we're making. That whatever their results were going to be their results no matter which kind of soda they drank. So we are going to run a simulation based on that assumption. I've got index cards right here in stacks of 20 that have all of the numbers from this table written on them. There's 20 numbers in the table. I have 20 cards, one card with each number. You're going to shuffle the cards together. So like upside down on your desk, mix them up. Make sure they're well mixed because we're going to randomly assign them to two groups again. You're going to deal out 10 of the cards into one pile, 10 of the cards into the other pile. You can go back and forth, or you randomly mix them up. You just split them up 10 and 10. It doesn't matter. Random assignment. The first group is going to be your caffeine group. So you're going to go to the pile that you have that you've called your caffeine group. You're going to flip those cards over. You're going to write down those 10 numbers here. And then you're going to go to your other pile. That's your no caffeine group. You're going to flip those cards over, and you're going to write those 10 numbers down. All right? Again, because the assumption that we're making is if they had a difference in heart rate of 8 beats, it wouldn't matter which group they were in. So what we're doing right now is saying it doesn't matter which group they're in. We're going to randomly assign them to these two groups, and then we're going to recalculate the average. All right? So once you have these 10 numbers, you're going to add them up and divide by 10 and write that number down out here. After you have these 10 numbers, you're going to add them up, divide by 10, and write that number down over here. That's where I want you guys to stop at for right now. It's just that piece. So I'm going to pass these cards out, and you will randomize. We can only give about 4 or 5 minutes for you to do this, so you need to do this quickly.
You guys why they?
You're welcome.
No, bro, like kind of saw these like look at it. Why not say that?
Mix them up. Make sure you mix them up really good. Divide it into 2 equal piles. 10 in each pile. One of your piles is your caffeine group. Write all those numbers down. Add them up and average them. Add them side by side. Then do the same thing for the other groups. No caffeine groups. Just make sure they're really mixed up.
Simone, do you have
Ready to go to the back table, man, and mix them up real good.
No. Stop.
Make sure you get the cards well mixed before you randomly assign them into 2 groups. Otherwise, it's not very random.
can't shuffle pieces.
I was gonna say these little
Yeah,
are like
they're not. Like
they don't
I just
shuffle
wish I
well.
had the skill of Joe.
you can show you just this.
That's fair.
I can teach you for real. Shuffle is actually
No, we're mapping.
Look.
Hey, stop.
So it's boom. And then
Leave me alone, alone.
you dynamite negative one, you ruffle.
I'm busy.
Oh, crap. They all shuffle down.
They work okay
Wait.
for a shuffle.
More specific somewhere.
Nice.
Well, now it's not random. You can see what numbers are going.
Well, no, she's got her. It's okay to flip them over as you're randomly assigning them. If you've mixed them all up, then you randomly put them into these two groups. Right. Got about 3 more minutes. Get them into the two groups. Write the numbers down in your table. Write down your caffeine group and your no caffeine group.
Survived the great hike.
What? Why survive the great?
They put hikes on the I Survived book. You know the fire I Survived book?
Split them equally.
Yes.
They put someone edited hikes in there.
There we go. Yep.
Wait, I can count.
I'm impressed.
Does this take time? Wait.
Once you have your two piles, you'll look at one pile, write it down on the caffeine row on your page. Then you'll add those 10 numbers up and divide by 10. Then you'll do the same thing for your other pile, your no caffeine group. You'll write those down on the no caffeine row. Then you'll add those 10 up and divide by 10.
We can start filling in our table.
Yes, please. Fill in your table with the 10 numbers. 10 for your caffeine group, 10 for your no caffeine group. Bless you. After you get your table filled in, you'll add up all the caffeine numbers and divide by 10. After you get all the no caffeine numbers, you will add those 10 numbers up and divide by 10. Write them down in the right-hand margin next to those rows.
I got a lot of high numbers in one group.
That's okay. That is funny.
What if I got 0 twice?
That's okay. You're going to get 0 twice because there's 2 zeros up here.
Oh, I see.
Yep.
I got 0.2.
As a difference.
Yeah.
Oh, we.
All right. All right. Is everybody at the point where they're calculating the averages?
Yes.
Yeah.
Okay.
Okay.
You got it?
Yeah, I was
Okay.
missing some numbers.
Did you find them all?
Yeah.
All right. Once you have all your numbers written down in the table, you can put the cards back together and put the paper clip around them. I'll come around and pick them up.
I'm not going on Miss Bowles,
Yes.
I did all the calculations. I left my glasses in my screen this way.
I can let you go through a little bit. You're going to want to hang around for this part, but there's still some participation.
After this,
Yes.
I think it's
All right. Does everybody have averages for their two groups? All right, almost. That's okay. What I want you to do now is just like on the original data where we did caffeine minus no caffeine, for your simulation, I want you to take the caffeine average and minus the no caffeine average. And you're going to write that down here for number 3. So do caffeine from your caffeine group minus no caffeine from your no caffeine group. You're going to get one number from doing that. That one number, you're going to come up and add to the dot plot up here. This is 5th period's dot plot. We're going to add on to this. Caffeine minus no caffeine. Yes.
Okay, who's on the chart?
That's okay, and that's really normal. Somebody had a difference of 2.6, which is normal. Just add it on to the end.
At negative what?
Hmm?
What was that last one?
This one over here is 2.6. Yeah. Yep, just one. It's just one dot. It's just one dot. What does each one of these dots represent? A difference of what?
Caffeine and no caffeine.
Caffeine minus no caffeine. The mean change. Do we know that the people in our caffeine group actually had caffeine? No. Do we know that the people in the no caffeine group actually had no caffeine? No. What did we do to get our two groups? Random shuffling. I'm looking for random and then a word that starts with an A. Assignment. Each one of these dots comes from one random assignment, and the difference of means that was calculated from that random assignment. One simulated random assignment and the difference of mean change in heart rate calculated for the two groups. What was the difference between the two groups from the real? 1.2. Let's find that on our graph. 1.2 would be about, I don't know, like here-ish? That would be 1.2. The 1.2 was the actual difference calculated from the experiment. This was the actual experimental result.
Which is different from our mu that we were using earlier.
Yeah. How many of our simulated results had the same difference or more than from the actual experiment? 5. Out of how many? 5 out of... Let's count the dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. So 5 out of 33. I'm not going to count my actual result. We're looking at what the simulated results were. If anybody had gotten right at exactly 1.2, if there was a dot right here, I would be including that. All right? So 5 out of 33. What is that as a decimal? It is something repeating. All right, so we're going to call this 0.1515. So if I change that into a percent, that's 15.15%, right? 15.15%.
And what is this 15.15%?
That's what we're going to talk about right now. Yep, no, that's okay. All right, so we're looking here at question number 5 now. What percent of the dots in the simulation are equal to or more extreme than the difference in means we found in the experiment? Yes, we had 5 out of 33, which was 0.1515. So we had 15.15%. the meaning of that percentage. We made an assumption before I gave you the cards and had you mix them up and deal them out. What was our assumption? That it was just a coincidence. So assuming caffeine has no effect, assuming caffeine has no effect on heart rate, there is a 15.15% probability of getting a difference in mean heart rate of 1.2 beats or greater purely by chance. Sorry for the messy handwriting. This is why I write stuff ahead of time as much as possible, because when I write on the fly, it looks like that. Yes, Kobe. So you're going to use 1.2 because this was the experimental result. This right here is the experimental result. We made an assumption at the beginning. That caffeine had no effect on the heart rate. That those people that saw a difference in their heart rate of 8, we're going to see that no matter which group they were in. That those people that saw a difference of 0 in their heart rate, we're going to see a difference of 0 no matter whether they got caffeine or not. So we made the assumption that it wasn't the caffeine that caused this difference. When we made that assumption and we just randomly assigned these results to one of the two groups, and we made our dot plot, what we found was that a little bit more than 15% of the time, the difference that we saw from the experiment happened just by chance. If something happens pretty often, and you see it happen out in the wild, are you suspicious? Do you think there's another reason for it? No, you're like, sometimes that just happens. No big deal. Whatever, move on. What about if something is really rare and you start to notice it happening over and over and over? There's probably some reason other than it's just random chance. If this is really rare to happen just by chance, and you see it happen here, and here, and here, you start to go, I don't think this is just chance anymore. They just had a big lottery drawing a couple weeks ago. It was like up in the, billions? So it took a while for somebody to win that, right?
Yeah.
What about if the very next week there had been another Powerball winner? And the very next week there had been another Powerball winner? That doesn't happen very often, right? If you start to notice somebody winning, and winning, and winning, and winning, do you think that it's still just chance? No. There would be another reason for it. If it's not happening by chance, it's happening for a reason. 15% of the time, this happened just by chance. Yes?
So, like, you know how lightning is random? So if you had a lightning rod, it always...
Yeah, I like that. Lightning randomly strikes, but if you have a lightning rod, it's going to attract the lightning. So you're going to see that area get struck more and more, and then you start to go, this isn't just happening by chance anymore. This is happening because I have the lightning rod in my yard. I like that. In a moment, yes.
Where did we get the 5 out of 33? I was doing the.
Yep, 5 out of 33 came from right here. There are 5 dots over here out of 33 dots total. Yep, that one over there.
So, okay.
Mhm.
In the future, our questions, when they are asking us to interpret the percentage, it's going to be talking about less than, greater than, things like that.
When we're looking at simulation data, yes. When we're looking at simulated data. All right. Do you think that the difference in pulse rate that we saw from the experiment, that 1.2 beats, was because of the caffeine, or do you think it happened purely by chance? Do you think it happened by chance? Do you think it happened by chance? Yeah. I think there's probably sufficient evidence here to say that this was probably just by chance. So, was this due to the caffeine? Probably not.
And is our 15.15%, is that factoring into our decision that we're making here?
Yes.
Because it's such a low percentage of greater than or more than. Like, what if there was a lot more dots?
We're going to look at that.
Okay.
Let's get this written down, and then I will go into that a little bit more. An event that happens by chance almost or about 15% of the time isn't very rare. It was probably just chance. Ooh, I love that. I love that. Let's see if we can figure this out. I'm gonna take a break for this for just a second. We're gonna do a little thought experiment. We're gonna figure out how rare does something need to be before I start to go, I think there's another reason for this. I think it's not just chance. I've got a regular deck of cards here. I'm not showing anybody my cards. You can see the backs.
Magic trick?
Yes.
It's not a magic trick.
It's a stats trick.
It's a stats trick. I like that. It's a stats trick. First person to pull a black card gets $100. First person to pull a black card gets $100.
Morning, guys. Let me go first.
What's the chance you pull a black card?
50-50.
50-50.
Truly?
Do we have to
How is it 50-50?
There's third.
Okay,
Half the deck is black, half the deck is red. Did you get a black card? No $100 for you. Who wants to try next?
Does it have to be off the top of the deck, though?
Gotta be off. I mixed them up before class. I have no idea what order they're in, but yes, you gotta pull off the top of the deck. Solid.
No, we're about to get
Yeah, no cheating.
You get a black one, split it.
Hold on. You already pulled a red card. We said it was a 50-50 chance.
probability reset?
Probability resets every time. So you had a 50% chance, but what's the chance that 2 red cards get pulled in a row? 25%, right? 50% times 50%.
Not quite 50.
Yeah.
25%.
It's actually exactly 25%.
What do you mean?
Probabilities multiply. If it's a 50% chance of the event happening first, if I had him put his card back in, it would be 50%. If I had him put his card back in, it would be
All
right.
When did he put his card back?
You're right, I didn't, but I was going to have him put it on the bottom, so there was no chance that one got pulled.
Well, statistically proven it'll be on the 6th card. So that's 4 right here. I'm gonna let Simone go, and then I'm gonna pick the next. I'm gonna go. I wanna go after the next person. I'm statistically.
Guys, you're only getting pipe bugs.
From the bookstore.
She stacked it. There's no way. I would love to go. I've statistically done.
Louder.
It's all red cards.
It's all red cards. Why do you say that? Are you accusing me of cheating?
Yes.
Why?
Because the chance is so low that it's not a possibility where it's like outside.
What do you mean by the chance is so low? Explain that to me.
The chance of you getting this many red cards in a row is very low.
The chance of getting this many red cards in a row is very low. And so you came up with a different explanation for why everybody was pulling red cards. Not just chance anymore. But now you came up with a different reason in your mind.
Oh, because also the chance that you're gonna get this $100 is very low.
Okay, that's a.
Solomon's right. They're all red. My point though, how many red cards did it take before you started to actually question that I had only put red?
I think 4 or 5. I think 5 would get some.
4 or 5?
Exactly.
All right, so it's a 50% chance that you pull a red card, right? Doing that 4 times, 50% each time, we're multiplying our probabilities together. I come up with about 6%. So there was a 6% chance, just a little bit more than a 6% chance, that the first 4 cards were red, just by chance. Normal deck of cards, I mix them up. It's a 6% chance that the first 4 cards are red cards. That's about where y'all started to get really suspicious. You said 4 or 5 cards. That's where our threshold is. It's about 5%. So in between 4 and 5 cards. If we had seen a result from doing this simulation that came out with less than 5%, if this happened less than 5% of the time, just by chance, then we're like, I think there's another explanation for this. Just like what happened with Solomon. He's like, I don't think you're being honest with us. I don't think this is a regular deck of cards. Because this chance of happening just randomly is so low.
Should we be writing this down?
Yes, I would write this down.
Where?
It's down at the bottom in green. It's very small. If the percent is less than or equal to 5%, it's pretty unlikely to happen by chance. So in this case, we would have concluded it's probably the caffeine and not just chance. Yes.
If it's less than 5.
If it's, sorry, first person that asks to go to the bathroom can go to the bathroom, and we'll go from there. I can only send one person at a time. I was going to say, he asked first, you asked second.
When did you ask?
Before class.
Oh, before.
If our percentage, oh, that's, just take that pass. Right, make sure, marker, you need to write your name, date, and time on the pass. If something happens more than 5% of the time just by chance, we usually just attribute this occurrence to being chance. If the third person had pulled a black card, you wouldn't have thought I was lying, right? But when the third person didn't pull a black card, and then the fourth person didn't pull a black card, and then the fifth person didn't pull a black card, that's when we started to really go, something's up here. Something's not right. This isn't just chance anymore. Oh, right there. It's okay. Does anybody else have a card? Okay. All right.
So if it's over 5%, then it's a coincidence?
If it's over 5%, then we attribute what we saw to just being chance. If it happens less than 5% of the time just by chance, then there's probably a better explanation for it. All right. All right, last question on this page. Okay. So if something happens by chance, often, which in this case we're defining often as being more than 5% of the time, we're like, that probably just happened just because. It's a common occurrence. If it happens rarely by chance, there's probably a better explanation for it, other than chance. All right? All right, last question on the page. Mrs. Bolton did the same experiment, but with all her students. Among the 136 students that were randomly assigned to either caffeine or no caffeine, the mean change in pulse rate for the caffeine group was 2.8, and for the no caffeine group was 1.9. Is that evidence more convincing or less convincing than what I found in my original experiment?
Less convincing.
Ooh, I heard both answers, and actually, what's the difference between the two groups here? 0.9. 0.9. I think you could argue this either way. I find it a little less convincing because the difference isn't as big. The bigger the difference, the more likely it is to be due to something other than chance. If there's only a small difference between the groups, it's likely due to chance. But she had a bigger sample size. She tested more students. Yes?
I thought that was one of the reasons that it was less convincing, just because the sample size is bigger doesn't mean
So just because the sample size is bigger doesn't mean that it is statistically significant. But the bigger the sample size, like if I had done the whole school or the entire city of Indianapolis, like the more people that I have doing this experiment, the more convincing my results are, because I'm testing more and more people with this, rather than say, well, maybe it was just that group, right?
When are we gonna get our review like Tuesday?
The review, as of right now, I'm planning on passing out on Monday.
Oh.
Yep. So you'll get that the same day that you turn in your homework, and then the test will be Friday, so you'll have it in your hands for almost a full week. All right, are you guys ready to turn the page?
Yes.
Okay.
Thank you.
Why do they make our UNLV on Thursday and not English Friday?
I've been asking that question for many years at this point. Yeah, I really wish that they would do it on a Friday, and you guys could basically just start break earlier. But that is not my decision.
There's not like a voting, like
No. Dry erase marker, right there, you need to write your name, date, and time on there. All right, we're gonna flip this over now to page 25. Let's finish this up. We've got just enough time to finish. Things are statistically significant when the results of the experiment are unlikely to happen purely by chance. If it happens less than 5% of the time purely by chance. And we use simulation to determine how often this would happen purely by chance. If the results are determined to be statistically significant, then we say we have convincing evidence, not proof. We don't have proof, but we have convincing evidence that the treatment was the cause of the difference. All right, I want to look at another situation. The following is an example of A/B testing, which is a common data science practice among tech and marketing companies. Do you guys know what A/B testing is? We're going to give you two conditions, condition A and condition B. We're going to see how the group responds to condition A. We're going to see how this other group responds to condition B. All right, so basically it's a binary. The marketing team at Yelp came up with two new formats for displaying ads on its site, format A and format B. Before deciding on which format to use across the entire site, Yelp wants to test which format would get a higher rate of ad clicks from users. Why do they care about who clicks on the ad? Yes. You want people to click on the ad because that's when the person who has the advertisement starts to pay more money. If people click on their ad, they're more likely to purchase the product from that ad. So you want to increase your ad clicks because it increases your revenue. So what they did is they randomly assigned 50 users to see format A. on their website. And they randomly assigned 50 different users to see format B. And they ran this for a little while. So the people that saw format A, 21 of those 50 people actually clicked on the ad and followed it to that marketing website. So 21 out of 50, that's 42%. So a little bit less than half the people clicked on the ad. People that had format B, there were 19 users out of the 50 that clicked on the ad. So that's 38%. So what's the difference in click rate between these two groups? 4%. In your own words, explain what statistically significant means. What does it mean to say that something is statistically significant? That can come into play. What does statistically significant mean? That's okay.
Like the percent is big enough to make us think that there's another cause.
There's another cause other than what? Other than by chance. So statistically significant means it is unlikely to be occurring by chance. Do you think that the difference in click rates is enough to be statistically significant? Do you think a 4% difference between these two groups is enough to be statistically significant? Nope.
What percent would we consider?
Ooh, that's a good question. We're going to look at this here in just a second. Because the thing is, I don't really know how big of a difference would be a big enough difference until I run a simulation. And I see what happens if it was just due to chance. Once I know how often these different things happen just by chance, I can say how likely this difference is just by chance. Yes.
So for the last problem, it was like 15.5%, and that was like by chance, and this one is 4%, and it's also by chance.
So what the percent is measuring is different here. This right here is taking the proportion of people that clicked on ad A minus the proportion of people that clicked on ad B. That's not the same thing as how likely it is to occur. On our last problem, we looked at how likely was it that we had 1.2 beats or more just by chance. This is just a difference between the two groups. We just happen to be measuring those in percents here. So if you look down at number 3 shows the results of a simulation. They ran the simulation 100 times. So I want you to imagine there's 100 students in the class. And we took all of these yes-no clicks and randomly split them up into two groups. And then I had all 100 people come and put a dot up. Where is 4% on this dot plot? Yeah, like right about here is 4%, right? How many dots had a difference of 4% or more? Around half. Count them up for me. Count them up for me. You're not wrong.
I'm gonna let you guys count and I'll write down what you guys say.
How many dots are there? 42. There are 42 out of these dots. There are 100 dots total, so 42%. So starting with the assumption that if somebody was going to click on the ad, it didn't matter which ad they saw or which format they saw. And if somebody was not going to click on the ad, it didn't matter which format they saw. They either were going to click on the ad or they weren't going to click on the ad. The format didn't make a difference. With that assumption in mind, 42% of the time, there was a difference in these two proportions of 4% or more. Is that a very rare occurrence? No. So why do you think we saw this 4% difference between the groups? Was it because of the format? No. It was just random. 42% of the time, we would get the same difference that we saw from the experiment or more extreme purely by chance.
And we came to this conclusion because of our 4% as well as our 42%.
So the 4% is just the difference between the two proportions, group A minus group B. Then what we did is the same thing that I had you guys do here with these cards, only instead of with scores written on them, it was either yes, I clicked on it, or no, I didn't click on it. So we have 50 yes, no's for group A. We have 50 yes, no's for group B. Take them all, mix them together, redivide them between two groups, randomly assigning them. Because whoever clicked yes was going to click yes no matter what. Whoever clicked no was going to click no no matter what. That's the assumption that we're making at the beginning. Please make sure you guys get this into your notes. If you have not signed up for the AP exam yet, late fees start promptly at 2 p.m. tomorrow. You need to get in and pay for your exam before 2 p.m. tomorrow.